Hi everybody, my name is Martin Hron. I work as a senior security researcher by security vendor Avast, and this talk is going to be about broken IoT supply chain. But don't worry, it's not that high level as it might seem. Actually, it's pretty concrete, or there is going to be a very concrete example of one particular IoT device that is being broken because of an IoT supply chain. So traditionally, when we think about the supply chain, this may be one simple example. So you've got a box of apples and you need to get them to the customer. That's traditional producer-consumer relationship, right? So as simple as it seems, it's not actually that simple. So first of all and foremost, someone had to create that box, right, for apples. So we have a box factory as an input. Also, someone had to raise the apples. So meet Joe, he is a farmer and he raised the apples. But to do that, he needed some tools, right? So we have a hardware factory which provides him tools he needs to raise the apples. And obviously, you already see here it's even more and more complex. So the box factory and the hardware factory, they have their own input or inputs in this case. So in case of a box factory, it may be some sawmill, so that's the source of food, or steelworks for a hardware factory. Maybe it's not that obvious from the diagram here, but even the hardware factory and the box factory, they have a relationship, right? Because the box factory needs tools as well, and maybe they also need nails for the boxes to be created. So there are more, this is more than like a tree structure, a huge complex network of relationships between entities. And we are still missing one important entity or one important part here, which is the transportation. And we have like all different means of transportation, and all of this basically means there is another supply chain involved. And maybe the last thing and least obvious is that there is another entity that basically is a part of the supply chain, and that's a Joe. Because in terms of a risk management, all these relationships and all these entities are kind of a risk. So if anything gets broken in this chain, the chain somehow fail or get broken or won't function properly. So every single entity is kind of a risk. So let's move into one specialized version of supply chain, and that's a software supply chain. The software supply chain is kind of a specific, and the specifics here is that the transportation is much more faster, right? So in connection with this, I personally love this quote, which says a lot, and it's perfectly applicable to the supply chain or to software supply chain. Because the software supply chain, like the analogy with the previous diagram, could be the developer is Joe here. He creates a code which gets built on a built environment, which could be seen as a farm, which has its inputs, which are like development tools, operating system, open source libraries, third-party libraries, and even the physical input in form of a hardware for the built environment and built machines itself. And the output is some software package that's pushed out of the built environment into a distribution server and from there distributed to the users. As I said, the main difference is all these transportation techniques are much faster because it's usually over the wire, over the internet. And that also means whenever there is any broken link or broken relationship between these entities, it gets propagated very fast. You know that very well, especially in AV industry. If you push out a wrong update to the users, almost immediately many users get affected. So speaking about supply chains, you can think of risks as vulnerabilities. So basically there are, I would say, two types of vulnerabilities in supply chain, or especially in cyber supply chain, if you want to. So these vulnerabilities are either intentional or unintentional. I mean, intentional vulnerabilities are usually kind of an attack to a supply chain, or even exploiting the unintentional vulnerabilities. But generally, a supply chain cyber attack is an attack that seeks to damage an organization by targeting less secure elements in the supply chain network, and very often, for example, to steal intellectual property from the company. We won't go any further with the supply chain cyber attacks. We will more, because that's completely different talk, we will more focus on, let's say, unintentional vulnerabilities in supply chains that are usually present without even anybody knows about it, right? Or knowing about it. So one more thing from the perspective of attacker, like the reason why attackers attacking supply chains and why we are also seeing so huge spike in supply chains recently is because you get a huge volume of victims very easily and with a very reasonable price. Sometimes the price is even zero, right? It depends when you attack, where exactly in the supply chain are you attacking to. So if you are as an attacker attacking to a very, let's say, low tiers of a supply chain, so that's the place where let's say the upper tiers share the most common entities or if you wish components, then you'll get better results. You'll get a huge outcome out of it. So as I said, we will focus more on the security of IoT devices and the supply chain with unintentional vulnerabilities in this case. When we're speaking about IoT devices in general, I think we are living exciting times. We are at the brink of completely new era because IoT devices are slowly getting everywhere. It's like the one phase of evolution, so you can think of it like there were many different important events in planet's history that basically meant a huge step either backwards or forward. So maybe the IoT could be one of these events, right? But I think we got from the evolution already into a revolution in the case of IoT, because if you think about it, the IoT is everywhere and we are putting more and more smart functionality into devices that don't really need them. I think that's insane. Like the explosion of number of IoT devices and the types of IoT devices is really, really huge. But it obviously comes with its downsides, right? So speaking of IoT, we have 4 main problems right now. Because the IoT is still, like from the security perspective, the IoT is still like in its infancy. So we have like 4 most prominent problems out there with the IoT. The first one is out of the box problem, which basically means that many of these IoT devices are created in a way so they are easy to use. It's like plug and play. But there is a problem with that, because they usually works like a prominent example could be router. You take the router out of a box, you connect WAN and LAN interfaces, and it just works. Usually it doesn't need any setup. So many of these devices end up with the default configuration, which can be pretty risky, because if it's a default configuration, it's usually documented in a manual, and if it's in manual, you can definitely find it on the internet. The second big problem is most of these IoT devices are using outdated protocols. And the reason for that is probably because most of these protocols came from the pre-IoT era, from the era of SCADA and industrial automation. And also at the beginning, most of these IoT devices were pretty limited in terms of computation power. I think it's not the case anymore, but still we are dealing with the IoT devices which are using, for example, Telnet as a communication protocol without any authentication, or another plain text protocols. And that could be a huge problem as well. Even modern IoT devices, sometimes they are just equipped with the debug interface or debug telnet open unintentionally because somebody forgot to close it. There is also the problem of volume, and it basically builds on top of the previous two. So if you have that poor security in IoT devices and that a huge amount, if out there is a study which says that by 2025 there should be around 21 billion IoT devices out there. And what it's more important is that 95% of them will be other devices than computers and phones. So we'll get like 21 billion devices with no screen or almost with no screen, using weird protocols with questionable security. That could be a really huge problem. And the fourth problem which we are interested in this talk is the problem of the supply chain. So many devices are being white labeled or share common components, and if there is any security failure anywhere in the supply chain, it gets pretty fast propagated and will scale at the end. The problem is we don't have really proper frameworks to let's say do a proper assessment of every input or security assessment of every input into our own supply chain or into our production. So that's a huge problem, and especially in cheap devices, nobody really does the security assessment or any, let's say, QA on the output. So this could be a very good example of how it looks like. So you see 3 cameras, they look alike. You should be thinking these are from the same factory, from the same production line. The truth is these are completely different cameras from 3 different vendors, but obviously they share common properties. And in this case, the common properties here are the DPS, so the board inside, also the OS, obviously the main CPU, which is Ingenic T20, I think, in all 3 of them. And it's obvious that they came from the same factory, they have the same drivers, they are built on the same or similar SDK. And if you open them and connect to a debug port, you can easily, basically you can easily through the debug port get a root with the same password in all 3 of them, like to a certain version of a firmware where they realized that that's an issue and change that. But yeah, that could be an example. So I like to show this picture during my talks because this is my mental image how the IoT security looks like. And to be fair, it's getting better. I think it's getting better. we are getting like more new stuff, more authentication schemes, proper encryption, but still there are holes, and these holes are usually coming from the problem of the supply chain. So it means there are usually the debug headers, non-restricted debug headers, or even the open telnet protocol on device that seems to be pretty recent and with decent security, or even the update of the firmware on the device is unsecured, even though the device has a proper security and uses TLS and certificate pinning. So we are not still there, but hopefully we are getting there. And to illustrate the rise of the number of the devices, I've done several years, I think 3 years ago, I done this research on MQTT servers that are widely available on the internet with no password at all. And it turns out that the number of these servers is rising over year is rising, and you can see it almost resembles the rise of a number of IoT devices. And the reason for that might be that MQTT servers are usually and very often used for integrating the IoT devices from different vendors. So now let's get to the main point of this talk and main thing I want to tell you. The one particular device I was speaking of at the beginning is GPS tracker. So the GPS trackers are basically devices often targeted at the children, elderly people, or to secure your car, or for you to know where your pet is. And they are often being marketed as bringing peace of mind. They are usually pretty cheap. These are like examples of these devices, so they really come in different shapes and colors and versions. So you can see there is like watches for kids equipped with the GPS trackers. There is a GPS tracker for your key rings, and the right one is a GPS tracker for car, which has even the ability to control your immobilizer, so you can basically kill the engine remotely through it. So the whole infrastructure of the GPS tracker usually works like this. So there is a GPS system with the GPS tracker on the input. The GPS tracker communicates through the GSM or mobile network somehow, either through LTE or GPRS with the cloud. And then on a user-facing side, there is that web application or mobile application that user uses to control the tracker and to get data. So inside of a tracker, there is usually like 3 distinct and important components. One is system on chip, or if you wish, main processor. And then there are 2 modules. One is for GPS and the other one is for GPRS or LTE. It depends on the version. And these are connected together by using a serial buses, usually. So let's have a look on one real GPS tracker and its analysis. So we started with this one. It came from eBay for $43. It was a nice package, and the onboarding process itself is pretty simple. But what I like to mention here is that for a first use, you need to log in by IMEI number. Or actually, it's not the IMEI, it's just a part of the IMEI. So you have some ID which is on the box, and you have to use that to log in into the application for first time. There is a version obviously for a web, and then there is also the Android and iOS application. What is also pretty interesting is that the default password is preset to 123456. That's exactly the case of an out-of-the-box problem, right? What's more concerning here is that user can't really create his or her username. So, or the only way how to create a username, you need to directly contact the reseller to create it for you, which is kind of a strange. So it's pretty obvious that most of the users are going to end up with the default password and the ID as a login name. So when you go to the web application, you see several red flags already here. So the web application is over HTTP, no HTTPS is available, so anything you type in goes unencrypted through the network. When you look into the traffic here, you can easily see it uses standard AJAX JSON scheme for communication, and you can see that after the login you'll get your user ID and the device ID. The device ID number doesn't have anything in common with the email number. So this is how it works on the web application, but we will dive more into the Android application, because this is basically just a subset of what the Android application does. So when you open the interface on the web, it looks like this. It's pretty standard. You can issue a commands to a tracker, so you can, for example, make the tracker to call another number or to send an SMS from here, or you can even upload a firmware to a tracker. So this is a close-up. You see that the IMEI number, is not actually the real number. It's just a part of it. So that's the ID which is on the box. And if you open the tracker, you see there is like the full email number and the ID. Just a primer how the email number works. It's basically very similar to MAC addresses. So you have like the prefixed part, or the prefix, which is basically allocated by region, by vendor, and by a particular product. Then there is 6 digits of serial number, which varies among the devices, and then there is a control digit or control number at the end. So if you map that into a number we had, you see that the 1703 is probably fixed prefix, and all these devices in the same batch will share this prefix. So from that you can also see there is one simple attack you can issue, and that's basically the enumeration attack, because like enumerate through 1 million possible serial numbers is not that hard, right? So let's have a look into an Android application and its communication with the cloud. So this is how it looks like. It's pretty standard. Again, you can log in using either ID or your username and password, but as I said, you don't have a chance to create a username by yourself. So you are stuck with the device ID. When we put this application into APK Lab IO, which is a nice tool we developed at Avast, which is kind of a threat intel platform for Android applications, and what it does, it basically runs the application inside the emulator and create a final report about basic features of the application. So you'll get the static features as well as dynamic. So you can see here you can see here that it communicates with this endpoint. So it talks to Open API v3 ASMX with the command login, and the whole payload is unencrypted. What's important here, you can see, as I said, because it's HTTP, you can see like the username and password unencrypted. But what's pretty important here is this key at the end, and this key is basically baked into the application, so it's constant. It doesn't change with every login, so that's a constant key you need to provide. So after the initial, let's say, reverse engineering, we set up a real proxy, so we can see the real traffic from the real application when somebody is using it. And we'll get this Wireshark log, and it basically proves everything I said. So you can see that the Open API v3 is the final endpoint for all the commands that the device is able to pursue. You can see that it started with login 3 version in this case. And if you look into that particular HTTP request, you can see it's basically the post form with filled in these information and the key at the end. So this is all you need to log into the API. And because the password is constant, it's pretty easy. Yeah, this is a close-up, so you can see it better. The password is 123456. The name is the ID. Login type basically just distinguishes between the login by ID or login by username. And yeah, what's important here to mention is the key. Remember that. I will come to that later. So, and this is the response when you do a login against the endpoint. And you can see you'll get few more detailed information about the tracker, which is the model, also the model encoded in, like, let's say, decimal number. And then this key is a session key you should be using for any other request to the rest of the API. So this is, for example, way how you can get the last position, so the get tracking info. And by issuing this command or this request, you'll get for that particular device ID, you'll get this, which basically says what was the last position recorded for that particular device and the battery status. Okay, so let's have a look how the tracker actually talks to a cloud, because that's another path we are quite interested in, right? So what are the options if you want to sniff this traffic? Actually, there are several options to go. Probably the most obvious is to set up your BTS station to sniff the traffic, but you can do that definitely. But we found out that there are more, let's say, there are easiest way to go. And we decided, because the tracker was pretty big and was nicely, like the PCB was nicely accessible, we decided to sniff the serial bus between the GPRS modem and the main CPU. And because all the data that goes to a cloud, the data has to go through the GPRS modem as well. So we opened the tracker and we found out that there are two sets of test pads, nicely labeled. So it turned out that one of these sets is for GPS modem and the other one is for GPRS modem. So by trial and error, we found the right one and got all the traffic between the modem and the main CPU. But at the end, it turned out that there is even easiest way to go, or easier way to go. And we found out in a documentation pretty interesting SMS command, because the tracker can be set up by sending an SMS to it. So you can basically, by issuing this command, set up an cloud endpoint. So basically you can set up an IP address on the port where all data from the tracker goes. So that was the easiest solution for us, right? So we set up a proxy again. We use that SMS to change the IP address and port, and the tracker sent all data through us to a cloud. So we got all the traffic very easily without like dismounting the device. And what we've seen here is another plain text. So it turned out that the whole communication protocol is basically based on these texts or comments, and what you definitely what you can't see here, and actually what's not here, is any kind of authorization. There is no password at all. And you can see it's pretty obvious what the command does. So you see the ID at the beginning, then size of the command itself, and the command. In this case, this command tells the tracker to call, to dial up this particular number and make a voice call to this number. So just by issuing this command, you can easily spy on the owner of the tracker, and using different various commands like this, you can basically even spoof the location of the tracker. You have, if you manage to get into or tap into the communication between the cloud and the tracker, you are on full charge, and you can do whatever you want. So, and as I said at the beginning, because we did that sequential or enumeration attack on that prefix, just to have a clue how big the problem is for this particular vendor, we found out that there were like 231,000 devices with default passwords, and for 167,000 we were able to obtain the last GPS location. It also turned out that there are 29 different models of trackers, so this cloud is being used for all the different versions that this particular vendor sells. So this is just how big variety of devices we are talking about. And this is a map for this one particular vendor. You can see there is not many of them in the United States, but these devices are definitely being used out of China. As you can see, there are pretty heavy load of them in Europe as well. And when you put that API endpoint we've seen in previous slides into a browser directly, you'll get this nice self-documenting UI. So basically, it gives you all the commands that the cloud infrastructure is able to do, and there is also a link to basically this conforms to a SOAP protocol. So you can, using tools for SOAP, you can basically get the whole API very, very easily. So there is one important thing here. So as I said at the beginning, there is the session key you need to put to every command of the API after the login. So you need basically two numbers, because the time zones doesn't really matter. You need a device ID and then the key. The problem here is that we found out that if you put the baked-in key instead of a session key, it works too. And in case of this command, it gives you a nice overview of all the pictures taken by this particular GPS tracker, because in this case it was a GPS tracker with the camera, and also very convenient image URL. You can get all the pictures. So basically it reduces only to knowing the ID of the particular device. But because the ID is again only 6 digits long, you can easily enumerate all of them, which is a huge problem. And by diving deeper into the applications, we were trying to find application with the same static baked-in key, and it turned out there are like 75 of these applications in our database already. So that basically means that there is probably more to this story. So it seems that this cloud infrastructure is not used just by this particular vendor. So we did a kind of a hack. We did a virtual research on this particular device. So basically what we did is we found another tracker on the internet, and just by trying to get the home page and trying to get the manual from the internet without like really getting the device itself, we tried to assess the security and find out if it shares the same cloud. So we found the application. On the homepage there is a link to a GPS tracking system, which is the web version, and also to an Android application. So it was pretty convenient. We dive into an analysis straight away because we didn't have any like real ID to use. We just typed in like random number into a login form, and we were trying to see what's gonna be the traffic going out of the application. So this is the application. We put there our fake ID, and this is the analysis from the APK Lab IO, and you can see here thing that basically proves our suspicion that the name of the endpoint seems to be same. Open API v3 ASMX. So we open that URL, and you can see it's almost identical to a previous vendor. And if you dive more into a manual or the leaflet for the tracker, you can even see there are similar SMS commands that basically set up the endpoint for the tracker. So we started to be suspicious about how all of this working. So we tried the first thing that basically was on our mind, which is basically searching the Google for Open API v3. And it turned out that there is a lot of links indexed by Google to a different, let's say, vendors and versions of that cloud. And we found this one where the browsing was allowed, so we got a pretty good picture about how the whole thing works. You can see there is even like the log directory and the directory with the ZK images, which in fact contain the images from the trackers. So it was browsable. We got everywhere we want to. And we were particularly interested in the logs because this is usually a very good source of information. So we opened one, and there was some exception information record. But what was interesting for us was this particular information, which tells us the name of the binary that basically runs or operates the whole logic. So it seems it's a ASP.NET library. So we did it again. Google is our best friend. We tried to find another websites that share the same properties, and it turned out we found another site with the browsing allowed. So we got all the binaries from there. And by putting them into IDA, we found out that there is one particular binary which is named send comments DLL, which basically contained a lot of supported models of GPS trackers and their protocols. That basically means that this API and this cloud infrastructure is very, I would say, thorough, and it implements a lot of different models. So it's heavily compatible with all the hardware on the Chinese market. And from that, we deduce this name of hardware manufacturers and affected models. Let's get back to an API for a moment. Remember this? So you can see there is that user account ID. But this is somehow strange, right? Because we didn't create any user account because there is no possibility how to do that. So I was quite curious what does this mean, right? So it turned out there is an API function that tells you a user info by user ID. So we put there the user ID and again the pre-baked key, and the output was like this. Now you can see it's definitely not my account or account of my tracker, but there is this login name, right? So once you put that login name into a login form, in this case login by an account, you'll get this. So basically you get the administration interface of a vendor who sells these trackers, and you can do whatever you want from here. You can export everything to Excel, you can reset the password, you can even charge the user if there is any charge policy, or if it's running on LTE plan, for example. This is really bad. And you can see there is that number of trackers for that particular vendor, which is like 10,000 trackers. So we were trying to reach out to vendor, but unfortunately they didn't respond, but they were slowly fixing the issues anyway. And we found out that they introduced this dialog. So whenever you are trying to use the password 123456, it asks you to change the password, or even if you are creating or if you are logging for the first time, it basically makes you to change the password. So from their side, this should be problem solved, right? But the problem here is the API is still vulnerable. So if you use the get device list, for example, with the username ID or with the user ID in ID here and the pre-baked key again, you'll get again a list of all trackers that belong to that particular vendor or user. So you can see here is like 13,000 of them in a nicely formatted JSON file. So we concluded that there are approximately 500 models and 30 plus cloud instances. These share the same API and vulnerability, and from that we roughly estimate that this affects almost 15 million of devices. And so this is a map of just a quick scan of another vendor. So you can see in this case there is a lot more devices in Americas or in United States and South America in general. And it also turned out that this is not a problem not only just in China, because we, for example, found this tracker which seems to be pretty decent. You can buy it on Amazon. It's almost bestseller. At the first sight it uses HTTPS, but if you run the analysis, you'll find this endpoint, which is not called OpenAPI anymore. It has another prefix, but the content is again the same. And all this led us to a company that basically is behind this all. And the company basically runs the cloud infrastructure, or on-premise provides the infrastructure to vendors or resellers. And everything is basically documented here, even the protocol itself, which is like the OpenAPI version 3. And there is really no mention, like no security at all. There is even there is basically no security. If you run through the documentation, it really doesn't have any security. And the most concerning thing is that down on these pages, you can find this proclamation that for the moment, more than 200 enterprise customers across the world chose our software, and over 7 million GPS devices were registered on our server. And that's information from 2014, so you can see that the issue is really huge. Okay, so how to conclude this talk? Actually, I didn't put any conclusion here because the research is still ongoing. Right now we are cooperating with more researchers who are basically doing very similar research on different other companies, but it seems that the problem is really huge. And all of this should just illustrate how bad the situation is and how the supply chain in this case can lead to a very serious security consequences and issues, and I would say at a huge, really huge scale. Okay, so I hope you enjoyed the talk, even though it was like packed with the information and I'm a little bit over time. So if you have any questions, don't hesitate to reach out to me either directly or wait for a Q&A session here at the Hacktivity conference. Thank you very much.